Namaste. A very good evening to all. I, the chairman of Pragna Foundation, Dr. Mahesh Arvin, welcome you all for today's talk of the week, Pragna Prerana. And today's talk is on complex analysis and its extensions, a deeper mathematical insight. And the speaker of the day is Dr. Nagarjun V. So before I connect him for the talk, I introduce him for all the audience. And it's my pleasure to introduce him. And I also to say that he was my student at Vijaya College for his when he was doing his undergraduation. Dr. Nagarjun V holds a doctoral degree in Nevanlinna theory from Presidency University. With over 8 years of teaching experience, he has established himself as a dedicated academician and researcher in the field of mathematics. His research interests lie in complex analysis, value distribution theory, and he has published more than 15 research papers in reputed national and international journals. In addition to his research publications, Dr. Nagarjun has presented over 5 papers at various national and international conferences. He has actively participated in more than 20 academic events, including seminars, workshops, conferences, and faculty development programs. Reflecting his commitment to academic growth and professional development. Dr. Nagarjun V currently serves as head of the Department of Mathematics at the Oxford College of Science, Bengaluru. With a strong commitment to academic excellence and institutional development, he actively contributes to academic governance and curriculum enhancement. He is a member of Board of Examiners at Maharani's Cluster University since 2022 and at BMS College for Women since 2024. So, with this brief introduction, over to Dr. Nagarjun V for the talk. Sir, on behalf of Pragna Foundation, I wholeheartedly welcome you for the talk. Over to Dr. Nagarjun V.
So, thank you so much, sir, for your brief introduction, and thank you for the wonderful opportunity to talk in Pragna Prerana, a talk of the week. With your kind permission, let me start our talk, sir.
Please.
So, I'll share my screen. So, a very good evening to one and all present here. I Dr. Nagarjun V, working as an assistant professor in the Department of Mathematics, the Oxford College of Science, Bengaluru. So today my topic is based on the complex analysis and its extension, a deep mathematical insight. Before going the complex analysis, let me introduce with some of the equations. So in your all mathematics students have come across the equations like transcendental equation, algebraic equation. So what are algebraic equation? An equation which contains only the variables is called as the algebraic equation. And transcendental equations are the one which contains the exponential, logarithmic, trigonometric, hyperbolic functions. If I consider an equation of the form x square minus 5x plus 6 equal to 0, I can find the roots of this equation by the method of factorization. So when I factorize this, you will be getting a roots x minus 3 equal to 0, x minus 2 which will be equal to 0. In the sense the value of x equal to 3 or the value of x equal to 2. So I will be getting the real roots by solving the equation x square minus 5x plus 6 equal to 0. So if I consider an equation is of the form x square plus 1 equal to 0. So the value of x square will be equal to minus 1 or x equal to plus or minus root of minus 1. We know the values of the numbers which is positive under the square root. For example, if I consider the value of square root of 25, it will be plus or minus 1. Under the square root, if I have a positive number, the value will be known. What happens if I have a number which is negative under the root? So it cannot be determined. Then the complex numbers have been originated. So if I solve the equation x square equal to minus 1, the value of x is plus or minus root of minus 1, which we call that as an imaginary numbers. So which is denoted by I. Then the complex numbers and the theory of complex has been developed. Therefore, the subject is called as the complex analysis. So, with a brief introduction of complex numbers, it is of course a classical branch of mathematics which was originated in 18th century, and many contribution has been seen from the notable mathematicians like Euler, Gauss and Riemann. And it also plays a very important and crucial role including analytical number theory. Number theory, conformal mappings, and the string theory. So complex dynamics and fractal imaginary have revitalized in the field of complex analysis. Not only this, complex analysis plays a very vital role in the field of engineering and physical sciences, which provides a powerful solving a challenging problems. It has many variety of application in the field of biology, medicine, and boundary integral techniques. And it also have very huge application in the field of fluid mechanics. We can study the fluid mechanics, the complex potential. There we use the concept of complex numbers. And if you have a real number is denoted by a letter R. Like whole numbers, natural numbers, we will be having some of the letters like R, N. R stands for the real numbers, N stands for the naturals. Q will be the rational numbers, and Q par C is the irrational numbers. Likewise, a complex number has also have a form. So complex numbers will be taking the form z is equal to x plus iy. Here x and y are the real numbers. When it's combined with I, it becomes an imaginary. So the complex numbers are denoted by a letter C, and it is of the form z is equal to x plus iy, where x and y are the real numbers and I is called as the imaginary number, which satisfies the equation I square equal to minus 1 or I is equal to square root of minus 1. And x is called as the real part, which is denoted by Re of z, and y is the imaginary part Im of z, which is denoted as Im of z. Here we note RE and IM of Z. The graph shows the complex plane. So the horizontal axis or the x-axis, we call it as the real axis, and the vertical axis or the y-axis, we call it as the imaginary axis. A point on the complex plane, which is denoted as z is equal to x plus iy, or it can be represented in the form of coordinate x comma y. Next will be the modulus. How we are going to study the algebra of real numbers. Likewise, we are going to study the algebra of complex numbers also. In that, the first concept will be the modulus of a complex number. If I consider z is equal to x plus iy, which is a complex number, then modulus of z will be equal to square root of x square plus y square. And always remember, the value of x square plus y square is always greater than or equal to 0. It will be a real number. Sometimes modulus of a complex number is also called as the absolute value of z. Next, algebra of complex number. We can add any two complex number, we can subtract any two complex number, as well as we can multiply or we can divide a complex number. So here we are going to consider, if I add or subtract, the minimum numbers required is 2. Like that, I'm going to consider two complex numbers, z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2. Then addition of these two complex number is denoted by z1 plus z2, which is defined as a1 plus a2 plus I times b1 plus b2. Similarly, the subtraction z1 minus z2 can be written as a1 minus a2 plus I times b1 minus b2. And if I multiply z1 into z2, the resultant will be a1 a2 minus b1 b2 plus I times of a2 b1 plus a1 b2. And if I divide z1 by z2, here the condition is z2 cannot be equal to 0. If z2 equal to 0, it will become infinity, which is not defined at all. So the condition for a division is z2 should not be equal to 0. z1 by z2 can be given with this expression, that is a1 a2 plus b1 b2 divided by a2 square plus b2 square plus the imaginary part. Next, conjugate of a complex number. So if I consider a real number 2, so the additive inverse of a real number 2 is minus 2. Like that, we will be having a conjugate of a complex number also. Sometimes complex conjugate can also be called as conjugate also. So the complex conjugate or the simply conjugate of z of any complex number is denoted by the symbol z bar, which is displayed there. So z bar will be defined as a minus ib. Here the thing is, we are going to change a sign only for the imaginary part, not with the real part. So if I consider a complex number z is equal to a plus ib, then its conjugate is z bar, which is equal to a minus ib. With respect to the modulus of a complex number, as I have told you, it is square root of x square plus y square. So it represents the distance from the origin to the point P on the complex number. In general, if I consider with respect to the real numbers, it represents the distance from origin to the some point on the Cartesian plane. Here, it's a point from pole to the point P on the complex plane. So in real, we call it as Cartesian. In complex, we call it as complex plane. Next, after this, we are going to represent a complex number in the form of polar. So hence it is called as polar form of a complex number. So there is a conversion from Cartesian form to the polar form by substituting x equal to r cos theta and y equal to r sin theta. Here, r is called as the radius vector and theta is called as the amplitude or the argument of a complex number. As the diagram says, so let me consider a point, any point P on the complex plane. So I'm drawing a point to the x-axis and as well as the point to the origin by using a straight line. Therefore, it forms a right-angled triangle. So, after finding a right-angled triangle, we are going to find the value of tan theta. Tan theta is opposite by adjacent side. So, how to find a polar form of a complex number? Then by using the substitution, x equal to r cos theta and y equal to r sin theta, where r is the square root of x square plus y square. How we will get this? I'm going to square it. X square equal to r square cos square theta and y square equal to r square sin square theta. We are going to add x square plus y square. X square plus y square will be equal to r square cos square theta plus r square sin square theta. R square will take common. We'll be getting cos square theta plus sin square theta. Cos square plus sin square will be equal to 1, the standard trigonometric identity. Therefore, x square plus y square equal to r square, or the r square can be written as square root of x square plus y square. And divide y by x. Y by x equal to r sin theta by r cos theta. R and r gets cancelled with each other. Sin by cos, we call it as tan. Theta equal to tan inverse of y by x. This as the theta is called as the argument of a complex number or the amplitude of a complex number. So we denote that theta has theta equal to AMP. AMP called as the amplitude of a complex number, or it can also be defined as argument of a complex number. This is all about the concept of polar form of a complex function. So I can have a limit of a complex function, continuity of a complex function, and differentiability of a complex number. Also, whatever the calculus part we are doing with respect to real numbers, the same thing we are going to deal with complex numbers also. So the limit of a function, so how it is denoted? So limit has z tending to z naught. Here the value of z is approaching to z naught, then the value of f of z will be equal to L. A function f of z, a complex function f of z is said to have a limit L. Has z is tending to a point z naught, then it can be written as limit has z tending to z naught, f of z value will be equal to L. So the next is continuity of a function. Any complex function is said to be continuous at a point z is equal to z naught, then it can be written as limit has z tending to z naught, f of z will be equal to z naught. Then we say that a function is continuous at that point z is equal to z naught. So differentiability of a function, here we are going to consider an open set. G is an open set. What is an open set? All its points are interior points. Then we say that the set is open. And we define a function f from open set G to the complex plane, complex number. F is a function from G to C. Then the function f of z is said to be differentiable at a point A. Then limit has, then it can be written as limit has h tending to 0, f of a plus h minus f of a divided by h. And this differentiability of a function is denoted by f dash of a, which is called as the derivative of a function of f of z at a point A. Analytic function. So after the concept of differentiability, it is very necessary to define a function called analytic function. Any function is said to be differentiable, any function is said to be analytic if it is differentiable at the point z is equal to z naught and in the neighborhood of z is equal to z naught. If I consider a function f of z, f of z is equal to 1 by z. I can differentiate the function. So f dash of z is minus 1 by z square. This function minus 1 by z square and f of z is 1 by z. It is differentiable at each and every point except at the point z is equal to 0. At the point z is equal to 0, it is not an analytic function. Apart from the point z is equal to 0, the function is analytic everywhere. So with this an example, we are going to define an analytic function. A function f of z is analytic if it is differentiable at a point z is equal to z0 and in the neighborhood of z is equal to z0. Sometimes analytic functions are also called as holomorphic functions or an regular functions. Harmonic functions, it is necessary to define an harmonic after an analytic function. So a harmonic function is defined like this. If it satisfies the Laplace equation, so the Laplace equation is defined as dou square u by dou x square plus dou square u by dou y square, which will be equal to 0. Here we are using partial derivatives, and this partial derivatives will be of second order because u is a function of both x and y here. So we are going to use a partial derivative. So after knowing the analyticity, so mandatory to understand the concepts of Cauchy-Riemann equation. Any function, complex function, let me say f of z is equal to u plus iv. U is a function of x and y, and v is a function of x and y. And these functions are differentiable. So differentiable means it should satisfy this condition which I mentioned earlier. Are differentiable, and this function, our real functions are analytic on a domain D if it satisfies the equation dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. If these functions are satisfied, then we say that the function is analytic. In the sense, ux equal to vy and uy equal to minus vx. This particular famous equation, we call it as Cauchy-Riemann equation. An equation which satisfies Cauchy-Riemann, we call it as an analytic function. It can be written in the polar form also by replacing x and y by r and theta. Next, Cauchy's theorem. So Cauchy gave a major work in the field of complex analysis. So Cauchy's theorem, it's a very important theorem to evaluate complex integrations. So if I consider a simply connected, so simply connected means any circle is also a simply connected region. In triangle or rectangle, all its are simply connected. If G is a simply connected, the integral over that gamma f of z dz equal to 0. For every closed curve, the curve should be closed, and there is a condition here, curve should be closed only. If the curve is not closed, if it has a branch cut, if the curve has cut in between, then Cauchy theorem is not verified. So f of z is analytic within and on contour, closed contour gamma, then the value of f of z dz equal to 0. This particular theorem, we call it as Cauchy's theorem. Then Cauchy's integral formula. So it is denoted by f nth derivative of a. The function will have a derivative up to nth order. F nth derivative of a equal to n factorial by 2 pi I integral over a closed curve gamma. Here also the closed curve is important. The curve should not have any branch cut. Then f of n by 2 pi I n factorial by 2 pi I f of z divided by z minus a whole power n plus 1 dz. So the value of n may be 1, 2, 3. If n equal to 1, we can find first derivative of f of z at point 8. If n equal to 2, it shows us the second order derivative. Then Morera's theorem. The Morera's theorem is the converse of Cauchy's theorem. What Cauchy's theorem? If the function is analytic within and on contour, then the integral value is 0. In Morera's theorem, if the integral value is 0, then we say that the function is analytic in nature. Next, after this, the major concept called this is the gateway to the higher level of complex analysis, which is the origination of Nevanlinna theory or value distribution theory. This is the main concept. What is the singularity? If I consider a function f of z, which is equal to 1 divided by z minus 3, at a point z equal to 3, f of 3 value becomes infinity. I don't have any value. It becomes infinite value. 1 divided by z minus 3 at the point z is equal to 3. This 3 is called as the singular point or the singularity, in the sense the analytic function will be seized at that particular point. That particular point, we call it as singular point or the singularity. So we can have many examples like sine z by z. At the point z is equal to 0, it becomes 0 by 0 form. If I apply the limit, the value will be equal to 1. That famous theorem you have already learned, which is called as the sandwich theorem. So you will be having the function f of z is equal to 1 by z. At the point z is equal to 0, the function will be seized. A singularity or the singular point is a point at which complex plane ceases to be analytic. Then such type of points are called as the singular point. For example, as I told you, at z is equal to 0, 1 by z is not analytic, therefore 0 is a singular point. So there are so many types of singularity: isolated singularity, removable singularity, or an essential singularity. We'll discuss all the singularity one by one. So a function f of z is said to have an isolated singularity. It should satisfy two conditions. It fails to be analytic at that particular point, and it should be analytic in the neighborhood of that point. For example, f of z is equal to 1 divided by z minus 5. If I substitute z is equal to 5, the value becomes infinity. Therefore, it is a singular point. 5 is a singular point. Apart from 5, whatever, if I substitute for the value of z, it is giving some finite term. In the sense, it is analytic. It is giving some finite term in the neighborhood of 5. Then such type of singularity is called as an isolated singularity, and that point we call it as isolated singular point. For example, next topic is removable singularity. A function f of z is said to have removable singularity if limit f of z has z is approaching to z naught, f of z exists finitely. If I consider sine z by z has z tending to 0, if I expand sine z using the Taylor series or the Maclaurin series expansion. So Maclaurin series, it is the expansion at the point about the origin. Sine z expansion is z minus z cube by 3 factorial plus z power 5 by 5 factorial and so on. So I'll divide that by z. If I consider a function sine z by z, it will be remaining with 1 minus the 1 power will be less. If I substitute z is equal to 0, the value will be equal to 1. So limit has z tending to 0 sine z by z, which will be equal to 1. Then that 0 is called as the removable singularity. Essential singularity, you have like this. A point z to have to be an essential singularity if f of z has a Lorentz expansion around the point z naught with infinitely many negative power terms. Next concept is poles. Poles are the one which is of the form f of z is equal to g of z divided by z minus z naught whole power n. If I get the value has infinity, then we call that as pole. So if n equal to 1, we call it as a simple pole. If n equal to 2, we call it as a double pole. If n equal greater than 2, we call it as a multiple pole. Here, g of z should be an analytic function and it is non-zero at the point z naught. Next is an entire function. A function which is analytic in the complete complex plane. It should not have any poles. I should not get infinity. Then such type of function, we call it as entire function, a function which is analytic in the complete or the whole complex plane, then we call it as an entire function. For example, every polynomial is an entire function, sin z is an entire, cos z is also an entire function. Meromorphic function, the exactly ulta of an entire function is meromorphic function with the one condition extra. A function f of z is meromorphic if its singularities are only the poles. So we have discussed so many types of singularity: isolated, removable, essential. Here the singularity must be a pole. So apart from pole, it cannot be satisfy any other condition. It should be pole only. Then the function is said to be meromorphic. For example, if I consider a function f of z is equal to 1 divided by z minus 1, if the value of z equal to 1, then f of z is said to have a pole of order 1. Then this function is meromorphic in nature. So this is an important topic, the Poisson-Jensen formula and the Jensen formula, which is the main gateway. Whatever we have discussed till here, these are all the basics of complex, and this is the main gateway for the Nevanlinna's value distribution theory. Before going to this, I'll introduce mathematician Nevanlinna. Nevanlinna is a famous Finnish mathematician who introduced his value distribution theory in the early 1920s. So sometimes Nevanlinna theory is also called as value distribution theory, which is the extension of the complex analysis, deals with the roots of the equation f of z minus a equal to 0, where f of z, it may be an entire function or it may be an meromorphic function. So this is the main formula, Poisson-Jensen formula, which is the gateway of Nevanlinna's theory. So here, log of modulus of f of z can be written as 1 by 2 pi integral 0 to 2 pi real part of re power I theta plus z divided by re power I theta minus z log of mod of f of re power I theta d theta minus summation k value ranges from 1 to n logarithm of modulus of r square minus ak bar z divided by r into z minus ak. This particular formula we call it as Poisson-Jensen. Here the function is f of z is analytic, a1, a2 up to an are called as the zeros repeated according to its multiplicity. What is repeated according to its multiplicity? I'll explain the sentence using a particular example. F of z, the function f of z is equal to z minus 10 whole power 5. If I substitute z is equal to 10, the value of f of z is equal to 0 to the power 5. So 5 times it is becoming 0. Then we call that as repeated according to its multiplicity. So the Jensen's formula is also just we are replacing the value of z to 0. Then the Poisson-Jensen's formula turns out to be a Jensen's formula. Again, here the zeros are counted according to its multiplicity. So this is the theory. So the value distribution theory, as I told you, which is the extension of complex analysis. This is the entire concept related to entire functions along with its zeros and multiplicities. So study of various polynomials of entire and meromorphic function aids in analyzing the solution of complex differential equation. So Nevanlinna theory or the value distribution theory, it's now being used in study of some Q-shift difference polynomials, differential polynomials, and differential polynomials. We are going to introduce some of the basic definitions and theorems before going to our main results or the main topic. The logarithmic function, the positive logarithmic function is defined as log plus x equal to maximum of log x comma 0, which is defined as log x when the value of x is greater than or equal to 1, 0 when the value of x greater than or equal to 0 and less than 1. And we can obviously see that log plus x can be written as log x can be written as log plus x minus log plus 1 by x. So the proximity function MRF, it's 1 by 2 pi integral 0 to 2 pi log plus modulus of f of re power I theta d theta. Next, the counting function. There are two different types of counting function. One is counting function of poles and another one is counting function of zeros. If it is capital NRF, it is the counting function of poles. If it is NR 1 by F, 1 by F, it is nothing but the counting function of zeros. And it is defined as integral 0 to R nt f minus n0 f by t dt plus n0 f into log R. Here NRF is called as the counting functions. And the sum of the proximity function and the counting function, we call it as Nevanlinna's characteristic function, which is denoted by TRF. TRF will be equal to MRF plus NRF, which is an important role in solving many of the theorems in Nevanlinna theory. So clearly the value of TRF is greater than or equal to 0, and it can also be written as TR1 by F minus A, which will be equal to MR1 divided by F minus A plus NR1 divided by F minus A. Here obviously A belongs to the complex number. So we can define the order of a meromorphic function, rho of F, which is equal to limit has R tending to infinity log plus TRF by log R, and hyperorder and lower order, which is the logarithm of characteristic function divided by log R, and lower order it is denoted by mu of F, and hyperorder it is rho 2 of F. Sometimes it is also has rho of F, which is limit supremum as R tending to infinity log plus TRF divided by log R. In lower order, we use only one log plus. In hyper order, we are going to use two log plus. So the Nevanlinna's first fundamental theorem, it is defined as TRF is equal to TR1 by F plus SRF. So here the function f of z is meromorphic in mod z is less than R and it is less than or equal to infinity. Then SRF is called as the remainder term here. So if I have a three small functions, then Nevanlinna's fundamental theorem is given by Q minus 2 TRF is less than summation J is equal to 1 to Q in R1 divided by F minus AJ minus N1R plus SRF, where N1R is called as they counts the multiple pole points of f of z, and SRF is the remainder term, and the function is obviously meromorphic in the finite complex plane, and AJ are complex numbers which varies from 1 to Q. This is the second fundamental theorem. So MRF plus summation J is equal to 1 to Q. MRAJ less than or equal to 2 TRF minus N1R plus SRF, where NR1R is given by this expression. So with all this basics, we are going to study one topic which is based on the difference equation. Very recently, Harina P. Vagamore and Naveen Kumar BN studied the results of Pulak Sahu and Himadri Karmakar and got the three main results, which is the main gateway for the recent developments in the Nevanlinna theory. They have done that. So if f of z and g of z be two distinct transcendental entire function, so transcendental entire function are the one which is not a polynomial of finite order, and p naught of z is not identically equivalent 0 be a polynomial, and the value of 2 degree of p naught less than n plus sigma plus 2. And this expression, if par n product from I is equal to 1 to d, f of z plus nj mu j minus p naught, and g per n of z product from j is equal to 1 to d, g of z plus nj mu j minus p naught, sharing 0 comma gamma. So if the value of gamma is greater than or equal to 2, then the value of n is given by this expression. If gamma equal to 1, n can be written as sigma plus d by 2 plus 6. If gamma equal to 0, n is greater than or equal to 2d plus 8. And then this one of the condition, if I consider f and g to be transcendental, then one of these condition is satisfied. F of z is equal to tau times of g of z, where satisfying the condition tau power n plus sigma equal to 1, and f of z equal to e power u and g of z equal to e power minus u, and p naught reduces to a non-zero constant, k and tau is a constant, satisfying the equation tau power n plus sigma equal to k square. So in his theorem 2, just they have replaced, they have studied what happens when the function is added with another one function f power m z minus 1 and g power m z minus 1. And the sharing in the previous theorem, it is 0 comma gamma, and here sharing is xi comma 2. Then the condition is also satisfied. They also proved the theorem what happens when the function is sharing a 0 cm. Then the condition, whatever I am displaying here, the condition what when gamma is greater than or equal to 2, gamma equal to 1, gamma equal to 0, the condition can be realized. Still, many more theorems or many more inventions are coming up with Nevanlinna theory. So I'm in this paper, I'm going to extend this theorem to meromorphic. The study is still going on. I have considered this paper. I'm very thankful to this opportunity given by our guru, Dr. Mahesh Arvin sir. I'm very thankful to you, sir. I'm very grateful to this for this wonderful opportunity to talk in Pragna Prerana, a talk of the week. Thank you so much.
Thank you, Dr. Nagarjun. Uh, after, uh, after a very long time, after my student days, I got an opportunity to hear about the complex numbers from my student during this talk. Very happy about it, proud on it. Uh, During this talk, Dr. Nagarjun started with a brief introduction to complex numbers and how we are going to study algebra of complex numbers, uh, amplitude of complex numbers or argument of complex numbers. He detailed on continuity of functions, defined analytic function, harmonic function, then explained about Cauchy-Riemann equation, further Cauchy's theorem, explained on the types of singularity and further about poles. So after introducing the basics of complex theory, he introduced Nevanlinna's theory, uh, the value distribution theory, and finally mentioned about the recent developments in the Nevanlinna theory. Uh, if any questions from the audience, you can raise it in the chat box. The speaker will definitely answer your questions. If not now, you can mail it. We will share the mail ID of the speaker, so definitely he will answer. So with this note, we will end the session. On behalf of Prajna Foundation, on my own behalf, on behalf of Pragna team, Pragna Prerana, and all the audience, I profusely thank Dr. Nagarjun for his informative and inspirational talk. Sir, thank you so much for the talk.
Thank you so much once again.
Thank you all for joining this session.